Hi everyone, welcome to lecture 10, and in this lecture we will discover the joint probability distributions. So far we have discovered and we have tried to understand how we can work with a one random variable, was just a single random variable, and we have learned that how we can calculate the probability of single random variables and how we can calculate the PMF of it, CDF of it, etc. And also we have learned some distributions. But in the real life examples, the probabilistic models often involve several random variables they have several random variables, and we can call them the random vectors. So we can give several examples for this kind of problems, like let's say for example the results of several tests in medical diagnosis context. Assume that you went to a doctor and they made some test on you, and in the results paper you can see that the number of red cells, red blood cells, and random of the white blood cells, etc. So you can see the many different results, right? So in this case, you have to deal with all these variables. And also another example is that the grades you got from the quizzes, midterms, homeworks, and finals, all of them can be considered as a different, the individual random variables, and you have to deal with all these things to calculate the some probabilities. And other examples from and another example is the exchange rate for the dollar, yen, euro, pound, sterling, and yuan today. So if you want to associate all these things with some other results, you have to think all these things. All this, the dollar, yen, euro, pound can be considered as random variables, and you have to deal with all of them all together. Okay, because one will affect another, and another one will affect each of them, etc. Also, the values of the several stocks in the stock market today. If you know the dynamics of the stock markets, you will see that there are different variables can affect the stock price. Like that is the open price, closed price, the volume, etc. Okay, all these things will be considered as a different random variables, and we have to work all of them, and we have to understand the relation between those random variables, and all of them will affect the final results. Another thing is the workload of several Wi-Fi access points throughout the building. There are many different things can affect this kind of connections, right? So that's why you have to learn and you have to analyze all of the random variables to finalize your work. So we can extend these examples, but try to understand the logic behind the different random variables. Remember that we have just work with the random variables, and we call it as a x, right? So instead of x, assume that we have x1, x2, x3, or x, y, z. So there are different random variables, and these things will be connected with each other, and that's mean each random variables will affect the probability of the other ones. Okay. Or in other words, the probability of one random variable will be shaped based on the probability of the another random variables. So we want to consider the probabilities of the events involving several random variables. So again, remember that, assume that we have an event A, and these events will be affected by the X and Y random variables. So you cannot calculate the probability of A based on X, but also need to consider the Y, okay? So we generalize the concept that we use for the single random variable. So actually the things is same logic, or they shape in the same logic. If you understand the basic logic behind the single random variables, you can also generalize for that logic for the different random variables. First, we begin with the two random variables. Of course, there might be more than one, but just to make the things easier and more concrete, we will assume that we have only two random variables, which is x and y, and that is called the bivariate distribution. Okay, so we have just two random variables, and we will learn how we can deal, or how we can calculate the probability if we have two random variables. Let's start with a discrete case and assume that the x and y are discrete. Okay, the calculating probabilities of the events involving only one of them, say x, was easy because we have just learned these things in the last 9 lecture, right? We know how to deal with the one single random variables. Just to remind you, we can assign a probability p of fx, which will be greater than or equal to 0, to each number x in the range of the random variable x, right? Remember that the x can take like 1, 2, and 3, and we know the associated probabilities for these values, right? That is the x, the capital X represent the random variables, and the small x's represent the possible values that random variables can take, and we have some probabilities, the associated probabilities like 1/2, 1/4, and 1/4. Okay, so we know how we can deal with this kind of random variables. So these probabilities define the probability mass function. So remember that from the previous lectures. These are our PMF. Okay, and we show that the probability of x, which is actually the probability of the representation is the probability of that two parentheses, and inside x, the capital X, which is equal to x. So just try to understand what is the meaning of this. The x is the random variables, and the small x is the values. Okay, but that's representation a little bit tedious. That's why we just ignore that parenthesis and we use that one. So that's mean, like, which is equal to like the probability of x equal to 3. That's mean what is the probability of x being 3? Okay, that is the representation of the PMF. And just if you don't remember these things, please just revisit the previous slides. Okay. Also, how we can calculate the probability of any event with the probability of x, which is in the event A, that is equal to the sum of the probability of x, and x will be in A. What's that mean? Let's say for this example, let's say the event A has two elements, that is 1 and 2. That's mean I have to if I want to calculate the probability of A, I have to calculate first the probability of x is equal to 1, which is 1/2, and plus, which is this that is the summation. And what is the probability of A will be 2. So the x will be 2, the small x, which is the 1/2. So 1/4. Okay, so the probability of A will be 3/4. So that is the probability of x within A, and in other words, this is the probability of event A. Okay, and also we know that we have the summation of all possible probabilities will be the 1. Okay, so that is from the normalization axioms from the probabilities. So that is how we can do the things in the case of single random variables, okay, and in the discrete case. So now assume that the calculating the probabilities of events involving both of them is also easy. In this case, instead of having one single random variables, we have two random variables, okay? And let's call it the x and y. So follow the same steps as we did in the single random variable. Assign a probability, the p of x and y, which will be greater than or equal to 0, to each x and y pair, where x is in the range of x and the y is in the range of y. Okay, so something like that, like x, let's say 1 and 2, and y is 3 and 4. That's no. These probabilities define the joint probability mass function P of x and y. Okay, that is simply meaning that the probability of x and y, which is equal to the probability of x will be equal to small x intersect with the probability of x intersect y. Okay, and in other words, we can represent the joint probability mass function as the probability of x, which is equal to x, the capital X is equal to x, and y, the capital Y is equal to the small y. So that is the representation of the joint probability mass function. So in the case of two random variables, if we want to calculate the probability of any event, which is the probability of x and y will be in A, which is the summation of all possible probabilities of x and y. And also again, the total probability will be the 1. Okay, so the same thing. So which is the probability mass function for single random variable? Okay, that is a single. And in this case, which is for the two random variables. Okay, so remember the probability mass function from the previous lectures. We know the corresponding the values of x and the values of x and the corresponding probabilities, right? In the two random variable case, let's say that is the x and that's the y, and which is the corresponding probabilities. So, for example, this one represents the x is 3 and y is 0. So, which is simply the probability of x, which is equal to 3, and y, which is equal to 0, is something like that. Okay, something like that. Some numbers, some probabilities. So simply the main logic is, what is the probability of intersection of these two random variables? Okay, but in this case, in this example, what is the probability of x will be 3 and y will be 0. Okay, which is called the probability joint probability mass function. Okay, so that is the main logic behind the more than one random variable. So let me give you another example. Like, let's say this one, which is in this case that represents the probability of x is equal to 1 and y is equal to 4. Okay, and that number, which is the probability of this situation. Okay, so that is the main logic. Actually the principle is the same, the logic is the same. It can be seen a little bit complicated, but trust me, that is easy. Okay, just try to understand the logic. So if we know the probability of x and y, we can obtain the probability of x and the probability of y. Okay, so that means if you know the joint probability mass function of x and y, that means we can reveal the probability mass function of x and probability mass function of y. But how we can do that? We know that the probability of x, the PMF of x, which is equal to probability of x, the capital X will be equal to the small x. Okay, that is how we represent the probability mass function of a single random variable, which is called x in this case. And since x is the union of the disjoint events, x equal to x, the capital X is equal to x, and capital Y equal to y, as y ranges over all different values of y. So Let me concrete that one. Okay, first. Let me open a white page. And let's say we have X and we have Y. X takes the values 1, 2, 3, and 4. And Y takes like A, B, C, and D. Okay. So when X takes 1, Y can take A and B. And when X takes 2, that can take C. And um, when X takes 3, that can be C. And when X takes 4, the Y will take the D. Okay, so what is the all possible the pairs, which is 1A, 1B, 2C, 3C, and 4D, right? 4D. 4D. So there is another pair? No. Okay, so keep this in mind, okay? So that is how we can, how the relation between two random variables. Okay, just ignore this part first. And if I ask you, what is the probability of X, which is equal to 1? In which case the X takes the 1, this one, and this one, right? So let's say which is P1 and that is P2, the probability, which is P3, which is P4, and let's say that is P5. And I want to take, so I know the probability of, I know the joint probability, right? So the joint probability mass function of P of X. So I know this one. This one is like, which is equal to like 1A, which is equal to P1, okay, 1B, which is P2, etc. So I know the joint probability mass function of these two random variables. And I'm asking you, what is the probability of X is equal to 1? So in which case X takes 1? This one and this one, right? So I know the probability will be P1 plus P2. What is the probability of X is equal to 2, which is this one, right? X takes the 2 here, and the probability is P3. And what is the probability of X takes 3? This one, only this one, which is P4. And what is the probability of X takes 4, which is this one, P5. Okay, so I have calculated the corresponding probabilities for all possible X values, right? And what is that? That's actually the probability of, but that's capital X. So that is the PMF of X. So what I did, from the joint probability mass function, I have just revealed the extract the PMF of the X, right? So the logic is simple, easy. So here, actually, we are doing the same thing. Since X is the union of the disjoint events, right? Because we know that, for example, for this one, the X is the union of this two. So if I want to sum all possible values for the X, all corresponding probabilities of X, okay, I will get the PMF of the single random variables, right? So what I did, I just I just keep the same, the x values, okay, x values, and look through the all possible y values, okay, like 1a, 1b, the x is same, and y change. And the summation of them will give me the probability of x, which is equal to that values, okay? And that is simply the PMF of the x values. So let me clear that one. Okay, which is so okay. So the mathematical representation of this, what we did is, which is the joint probability mass function, and I will change the y values, okay, and I will sum up all probabilities for the different y values. Actually, what we did here, like, remember that. Y and xy. How can I reveal the PMF of x? Let's say x. First, I will look for the x is equal to 1. And what I'm going to do, I will change the y. Okay, I will change the y. And I will sum up them. Okay, and that will give me the probability of x, which is equal to the first value of it. Okay, so, and similarly, I can do the same thing for the PMF of y, right? What I'm gonna do, let's say y, it can take a, b, c, and d, right? So if I can calculate the probability of y is equal to a, y is equal to b, y is equal to c, y is equal to d, that means that is the PMF of the y. How can I do that? Okay, let's keep the y is equal to a and change the x values. So look for the possible x values. For example, for this one, which is only we have x1, right? So only this case. So the corresponding probability will be p1. For the b, only this case, which is p2. And for the c, we have two cases in which x is equal to 2 or x is equal to 3. So the corresponding probability will be p3 plus p4. And for this one, for the d1, the x can take only 4, and the probability is p5. Okay, so what did I do? From the joint probability mass function, I just revealed the PMF of x and the PMF of y. Okay, so, and they are referred to as a marginal PMF of x and y respectively. Okay, we call these things as the marginal PMF of x and y. So that is a more clear explanation. Let's say the x, here is x and here is y. X can take 1, 2, 3, 4, and the y can take 1, 2, 3, 4. Okay, so these are the corresponding probabilities. What I mean, like the probability of x is equal to 1 and y is equal to 1 is equal to 1 over 20, right here. The intersection of these two values, which is 1 over 20. Let's say I want to calculate the probability of x is equal to 1. What I need to do? I will keep this thing same, the x values as 1, and I will look over the all possible y values, okay, here. So in the case of x is 1, y can take 4 different values, 1, 2, 3, and 4, and the summation of these probabilities will give me the probability of x is equal to 1, which is 3 over 20. Okay, And the same thing for this one, which is the probability of x is equal to 2, which is the probability of x is equal to 3, which is the probability of x is equal to 4. And the same thing here, the row sums will be the marginal PMF of py. For example, the probability of y is equal to 4 will be summation of these guys, which is equal to 3 over 20. And the probability of y is equal to 3 is the summation of this guy, because if y is 3, and if I am asking the probability of y is 3, in this case, x can take 4 different values, and each of those 4 values, y is equal to 3. Okay, so I just need to sum up all this, the probabilities, that is equal to 7 over 20. Okay, and so in a summary, in a tabular form, the column sums represent the marginal PMF of x, and the row sums is the marginal PMF of y. Okay, so that is the basic logic, the main idea behind the joint probability mass function and the PMF of single random variables. And that is called, just remember that these are called the marginal PMF of x and marginal PMF of y. Okay, so this is the end of part 1, and we will continue with the continuous case, and we will use the same logic. So please take it easy and just try to understand the logic. Okay, I'll see you in part 2.